There's one more seat over here.
Another chair here too, someone else use this.
Hey, Valerie, is that roughly everyone?
Yeah.
All right. I'm so happy that we have Megan, soon to be Dr. Megan Masterson. She's at MIT, and she's in the last year of her PhD. And she has been working with Aaron Pratt, who is a world-leading observational astronomer, working on transients, multi-messengers. And I knew her actually from her papers even before we met, but we actually met this summer at a conference in Madrid, where she was one of the only few PhD students invited to give a talk. And I would like to describe her as a rising star in the field of observational astronomy, especially transients. And she already has produced very interesting, impactful research, including identification of a new population of IR selected, infrared selected tidal distortion events, and also she published a paper on the first JWST observations of TDEs. And also she published a paper in Science on the observations of millihertz QPO, for example, of a supermassive black hole in real time, which I think even as a theorist is extremely challenging. And today, I think we will hear more about all these topics. Yeah, let's go.
Okay, thank you, Teo, and thank you all for coming. I'm really excited to be here to tell you a little bit about the PhD work that I've been doing at MIT. And I'm going to be talking about broadly transient accretion onto supermassive black holes, touching on basically all of the topics that Teo introduced. So I like to get started with a beautiful image from JWST, just highlighting kind of the immense number of galaxies out there in the universe and the diversity of the sorts of galaxy shapes and properties that we see. But what we kind of universally know is that there's a supermassive black hole that sits at the center of each of these galaxies. And this supermassive black hole can have a significant influence on how the galaxy grows and evolves throughout cosmic time. And most of this sort of evolution that's coupled between the supermassive black hole and the galaxy, we think stems from black hole accretion. So as the black hole accretes matter, it also launches jets and winds that can impact the host galaxy. But actually what we've been finding out in the last decade or so is that the process of black hole accretion, despite us knowing about it for something like 60 years or so now, is actually kind of messy. And in particular, what we're finding is that time domain surveys, which are regularly monitoring the night sky, are revealing much more extreme and rapidly variable supermassive black holes than we previously thought possible. So this is one example, and it's an older paper now, but it's from the Catalina Sky Survey, which is kind of one of the predecessors, one of the first transient surveys that's going out and monitoring the sky regularly. And what you see is an active galaxy that suddenly went through this major optical outburst, where over the course of a year, it increased in brightness significantly and transitioned to a different sort of accretion state. And you might be asking, why is this so surprising? Well, the main reason I think that this is kind of a surprise to all of us is that these sorts of timescales that we expect these major changes to the accretion state around supermassive black holes to occur on is what we call the viscous timescale. This is basically just the timescale that sets how quickly matter can flow through the disk and onto the black hole. And this is something like 10 to the 4 years in AGN. So it's much longer than these sorts of transitions that we're seeing in these supermassive black holes, thanks to time domain surveys. Now, in addition, time domain surveys are doing something else that I think is really exciting. And they're unlocking a population of dormant supermassive black holes. So if you go out and you look at the night sky, roughly 1 in 10 galaxies will have an active black hole at the center, and the rest of them will be kind of sitting relatively dormant, similar to our own galaxy and Sagittarius A star. And in order to really truly know how galaxies and supermassive black holes co-evolve and to understand the population in general, we really need to probe this dormant population. And that's exactly what time domain surveys are allowing us to do, in particular through these types of events called tidal disruption events, which you're seeing a schematic of here. So tidal disruption events, or TDEs, happen when a star is kind of flung onto a highly elliptical orbit. It gets really close to the supermassive black hole. That supermassive black hole's tidal forces on the star actually overcome the star's self-gravity, they rip it apart, and they lead to basically this temporary accretion flow of gas that lights up these dormant black holes and allows us to see them for a short period of time. And so I'm really excited about using tidal disruption events to probe this dormant supermassive black hole population. It's kind of actually the dominant one out there in the universe. So my PhD has been focused on leveraging these time domain surveys to learn about black hole accretion, black hole demographics. And as Tejo mentioned, it's kind of been in 2 different parts. The first part that I'm going to talk about today is using rapid X-ray variability to probe regions very close to the supermassive black hole. And the second part that I'm going to talk about is completing our census of tidal disruption events, TDEs, using infrared surveys. And that's going to be kind of probing more of the nuclear environment, the larger scales away from the black hole. So let's get started with part 1. So part 1 brings me to, it's going to be a single source. We're going to really dive deep and understand this one supermassive black hole that I know there are people in this room that are very familiar with. This is 1ES 1927 plus 654, and I personally think it's the most crazy AGN we've ever observed. So prior to 2018, it was known as a type 2 AGN with no broad lines in its optical spectrum. And then in 2018, thanks to the time domain survey Assassin, we caught this major optical outburst from this source. And it almost looked like what we expected from tidal disruption events, where you see a fast rise followed by a slow decay. But interestingly enough, the source was already active. And what was truly the most bizarre thing about this object is that its X-ray spectrum changed dramatically. So to walk you through what this plot is actually telling you, the gray curve that you're seeing here, this is the data from before this optical outburst occurred. And this is kind of a relatively standard X-ray spectrum of an AGN. You have a disk that's producing UV photons. These UV photons are upscattered by this corona, which is this hot relativistic plasma full of electrons that are giving a little bit of energy to these UV photons, making them X-rays. But yet in the orange, you can see that in June 2018, shortly after this outburst started, we don't see any hard X-ray emission from a corona. And instead, what I think we're seeing is basically just a thermal black body stemming from kind of the inner part of the accretion flow, possibly some sort of hot super Eddington disk. And I don't have time to talk about it, but you're welcome to ask me questions. I spent the first couple of years of my PhD working on modeling this spectral feature that you can see, this broad 1 keV line, and we explained it as a relativistic outflow. I should also say, feel free to interrupt me throughout the talk if you have questions. Okay, so most of my work actually is not going to care about which of these 2 interpretations are indeed the correct one, and I think jury's still out. But 2 possible explanations to explain this event are that A, we have a tidal disruption event occurring in an existing disk, where if you smack basically a stellar debris stream into an existing disk, you'll shock the material, and this will lead to basically depleting the inner part of the accretion flow, and that will cut off the energy supply to this X-ray corona. And the other one was led here at CU Boulder, which is talking about flipping the magnetic flux of the accretion disk. And as that moves inward, you will basically naturally cut off the energy supply to your corona because you've flipped the magnetic fields, which are actually what's driving the heating process in the corona. So what I've been working on over the past many years, pretty much my entire PhD, is trying to understand the X-ray evolution of this system. So this is a 6-year X-ray light curve where we've dedicated tons and tons of resources to monitoring this event. And the optical flare decayed pretty quickly, but what we're left with is kind of highly variable X-ray emission. But to cut the story straight, to go straight to the point, by 2021, what we saw was that if I plot that same X-ray spectrum, in gray is your pre-outburst and in orange is your post-outburst in 2021, you're seeing that we've reformed the X-ray corona. And so we were like, yay, cool, outburst is over. I was a young, naive grad student, and I was like, okay, I want to understand the source in more detail. So I put in some more telescope proposals, and it was mostly focused on trying to understand the nuclear environment of the source and what triggered this sort of event. And I'm glad that I did that, because this is actually the data that we got back from some of those observations. And if you're not used to looking at AGN light curves, I just want you to take away that you can actually see these like sinusoidal signals. Most AGN do not show signals like this. They show kind of stochastic variability, and this is much more coherent than anything we usually see around supermassive black holes. So we call this a quasi-periodic oscillation. Essentially, it's a sinusoid where the frequency shifts like a little bit. And what's really exciting is that this QPO actually continues. So this is the next observation. The timescales are same on the x-axis. So if I flip back and forth between these and you have a really keen eye, you can see that the period has actually changed. If you can't see that, that's okay, because I can put it in Fourier space for you. So this is a Fourier transform of those two different light curves. And what you can see is that these peaks, these are the quasi-periodic oscillation that I'm talking about, that sinusoidal signal, and the frequency of this has shifted significantly. And
what is the quality factor of this?
10-ish, which is comparable to what you see in X-ray binaries. So the quality factor is basically how broad these features are, and it tells you about how many cycles you can be coherent over. So that is, if you plotted a sine curve on top of the light curve, it would be good for about 10 cycles, and then it would dephase. But yeah, cool. And it turns out that over 4 observations spanning over 2 years, we continually detect this oscillation, and the frequency does over like a factor of 2 change to the frequency. And it actually seems to be started increasing, and then now it's plateauing. And I have more updated data, and I'm happy to report it's continuing to be detected, but it's still roughly at this similar frequency. So that's not the whole story in this kind of late time state of this source. It turns out that if I now take the X-ray light curve and I overplot a radio light curve, what we saw was very little change to the radio emission until around the time the QPO turned on. And then we saw this major radio flare where the radio increased by a factor of like 30. And at the same time, one of my colleagues was doing VLBI observations in response to this flare. And what we saw was that we actually can see a resolved outflow. So this is a core subtractive radio image. You can see these 2 lobes kind of corresponding potentially to an outflow that's being launched, and we're actually seeing it in real time. And the speed is something like 0.2c, although the modeling is quite complicated. So I think this is really exciting. And if you take the similar turn-on times, maybe you can try to do some corona jet connections, because we think that the corona and the jet might be kind of coupled in some way, a way that's actually much better studied in X-ray binaries than it typically is in AGN. So one possibility for what's driving this QPO is some sort of oscillation in a newly formed corona. So I'm attempting to show you some sort of schematic that does this. And in order to change the frequency, you need to change the properties of the corona. And so if you make the corona smaller, you make these oscillations faster. And the same thing if you increase the temperature, because these oscillations are driven, we think, at the speed of sound, basically. And the sound scales with the temperature of the corona. However, we have essentially no method to constrain either one of these. So if you'll let me be a little speculative, the other way that you can try to explain this sort of oscillation is with a compact object near the event horizon. And this is really driven from analogies with what we call quasi-periodic eruptions, which are these hour to day-long bursts of X-ray emission that we think come from a compact object impacting a disk over and over again. And this is really exciting because we're going to have multi-messenger capabilities with these sorts of objects in the next decade. But QPEs are much further away from the black hole than we kind of need for these sorts of multi-messenger events. We really need to get closer to the event horizon for these new multi-messenger signals. And so one possibility to explain this sort of frequency evolution is that you actually have a balance between gravitational waves driving your source inwards and some sort of accretion-driven out spiral. So this is kind of motivated by a community of people who study double white dwarfs in our own galaxy. And what they see is that as these two sources become, their orbits become very compact and they actually start mass transferring, you're actually able to couple the angular momentum that you drive outwards in an accretion disk to the companion and lead to out-spiraling systems. And there actually are a handful of out-spiraling double white dwarfs that are known. So this is my kind of speculative potential thing that could be happening to drive this QPO. And the reason why I like this model is because we've made a prediction. So this is a LISA sensitivity curve where everything above this black line is what LISA expects to be able to detect. So LISA is an X-ray, or not an X-ray, it's a space-based gravitational wave observatory that will launch in the 2030s and be sensitive to the millihertz regime. And in particular, if you have a white dwarf in orbit around a supermassive black hole, like we predicted in 1ES 1927, it sits right in the sweet spot of where LISA expects to be observing, unlike these QPEs, which are a little bit too low frequency. Although potentially, depending on what their counterparts are, you might be able to detect them. And then, so I think I'm also excited for the future of LISA. It's also going to detect merging supermassive black holes. So this is a plot just showing you, these are different signal to noise calculations for different binary supermassive black hole masses, highlighting that we can see merging supermassive black holes in LISA out to really high redshifts. And I should say that I have also, during my PhD, worked on a binary supermassive black hole candidate. I will say after working on it, I think it's no longer a binary supermassive black hole candidate, but I won't say much more except that I think LISA is going to really help us detect and discover what the electromagnetic signatures to binary supermassive black hole mergers actually are. Okay, so with that, I'm going to transition to part 2, but I want to pause and see if there are questions on part 1. So we're going to move away from the black hole event horizon.
Find any correlation between the UV frequency and the UV flux?
The UV. No, the UV is staying pretty constant. So that's one of the other kind of puzzling things about this source is that it started to increase its X-ray flux, but its UV flux has remained pretty much the same.
So disk is not, that means disk is not changing.
Yeah.
If we assume that from the inner edge there is some somewhere which is triggering this QPOs,
Yeah.
it should change, then it doesn't explain it.
Well, we're not, so our observations are not probing the peak of the UV flux, right? We're like way out. We need to go much shorter wavelength, and that's just a part of the electromagnetic spectrum we don't have access to. So I would say it would be great to look for them, but there's literally, we can't do that in the UV at least. Now I will say the X-rays, the X-ray flux correlates with the QPO frequency, which I think is interesting. But I think we're really driven by the corona rather than the disk. Yeah.
So for the, you mentioned the QBEs.
Yeah.
Whatever the compact object or star that's
Mhm.
much bigger than this. I'm assuming the frequency is a little bit, it doesn't match up with LISA. Is that what?
Yeah, so they're more like microhertz.
Okay,
They're,
so we have pretty good constraints on the semi-major axis,
Yeah.
while it's in spiraling.
Yeah.
Okay.
so the period is pretty well defined. These are evolution over different periods. So these are
Gotcha.
two different QPEs. What we don't know in QPEs is what the actual the secondary body is. It's becoming, I think, more and more apparent that we think it's a star rather than a compact object,
So
which
it's
pushes you down into this regime. These peaks that get above the LISA sensitivity curve are only if you have like a 50 solar mass black hole,
Okay.
which I think is kind of unlikely just based on the observations of QPEs.
Going back to what the students did, the frequency is related to that, is correlated with like,
Yeah.
there a lag at all?
Not that we can tell. You mean between like hard and soft X-rays?
Yeah.
Okay. There is a lag. The lag spectrum is a little complicated. The soft X-rays, okay, the lag spectrum looks like a U, if you know what I'm talking about.
Yeah.
So the soft X-rays and the hard X-rays are both kind of lagging behind the like 2 keV period. So I'm working on an upcoming paper on this, but we're still working on the interpretation of the lag. But it's very short and it doesn't evolve over long time scales. So if you probe the lag at the QPO frequency and you probe the lag at low frequencies, they look identical with different amplitudes. So I don't really know what to make of that. I saw your hand.
Online question.
Yeah.
Can you explain one more time the potential mechanism for accretion driven out spiral? within the context of an accretion disk rather than a white dwarf binary?
Yeah, so it's a good question. So in the white dwarfs, what happens is that because white dwarfs are degenerate companions, as they lose mass, they get larger. It's this counterintuitive aspect. And what that means is that as they lose mass, they can continuously stay in contact with their accretion disk. And they can actually, basically, as you're accreting mass inwards, you're sending a little bit of angular momentum outwards. And so you can basically couple that angular momentum to the outer companion. I will have to say that doing that in a black hole, like in a supermassive black hole environment, is really uncertain. And in fact, one thing that I tried to do when I was initially doing this calculation is estimate, like, can you form a disk when you accrete off of the white dwarf onto the supermassive black hole? Like, can you actually transport this angular momentum backwards? And it turns out that the way that people do this in the double white dwarf community, you can't just extend this down to supermassive black holes, because the theoretical models actually break and give you, like, it's not saying that we can't do it physically, it's saying that we need new models to be able to test whether we can do it physically. Yes, there was something else I wanted to say, but I have forgotten what it is now. So it's a little bit tenuous, and I think there's more theory that needs to be done about these objects in orbit around supermassive black holes. I think there was another question. Yeah.
That's an exact question.
Oh,
So
cool.
I just want to go with question more around that. So they probably assume some analytic model to model these double white dwarfs.
Yeah.
And I'm guessing that just breaks down for your case.
Yeah.
You would have to calculate the precession ratio between gravitational wave versus your new
Yep.
white dwarf punching through white dwarf.
Yeah. It depends on the mass ratio. And as you extend to low mass ratios, the equations that people use in the double white dwarf literature just are not valid. But I will say, okay, this is what I wanted to say, which probably also helps answer this question, is like you can estimate how much angular momentum you need to transport backwards to offset gravitational waves. And that's a fairly straightforward calculation to do, and it depends on the mass transfer rate. And what we get is that to balance the gravitational wave in spiral, you actually don't need crazy mass transfer rates. They're high, but they're like what double white dwarfs we think reach at the peak of their mass transfer. It's like 10 to the minus 4 solar masses per year. So it's not unreasonable. Yeah, but I think motivates more theoretical work on these sorts of systems. Okay, cool. So with that, I'm going to move to lower energies and talk about kind of the nuclear environments around supermassive black holes and using infrared time domain surveys to find more TDEs. So as time domain surveys have kind of taken off and started to survey more and more of the sky, and we've gone through kind of major technological advances, we've started to be able to detect more and more TDEs per year. And I really think this is kind of bringing us to the TDE population era. So this is just a plot showing you the cumulative number of TDEs that we've detected to date. It's only up to date as of 2021. We actually have like 200 TDEs now. And you can see that the majority of them are found through these optical surveys. And that's primarily because in optical surveys, you can do really wide surveys, scan the sky very regularly, and go very deep. And that's much more difficult to do at like X-ray wavelengths, for example. And just studying the number of TDEs that we have is actually really powerful for telling you something about the supermassive black holes. So in particular, there's kind of two different regimes that we can learn about from studying TDEs. So I'll walk you through this really briefly. At the low mass end of just counting how many TDEs we see per mass of the black hole, we're sensitive to things like the actual supermassive black hole mass function, which is really uncertain in the low mass, like 10 to the 4, 10 to the 5 solar masses regime. And we're also sensitive to the occupation fraction. So how many supermassive black holes are actually in halos. At the high mass end, we're like fairly confident this is 1. In the like dwarf galaxy regime, this is really uncertain. So this is just showing you theoretical models. We're not here in terms of testing this with data, but we can really start to say something about what the occupation fraction is. And at the high mass end, what we can use is a steep cutoff in the rate of TDEs around high mass supermassive black holes to probe the black hole spin. And this primarily arises from the fact that for low mass black holes, the tidal radius is outside of the black hole's event horizon. So you see an electromagnetic signature. Basically, that's what we're all seeing. But when the black hole gets more massive, the tidal radius grows sublinearly with the black hole mass. And so eventually, you'll actually just swallow your star whole before you actually tidally disrupt it. And so at too high of masses, you wind up not seeing any sort of TDE. Okay, but in order to do both of these things, we really need to understand our observational biases and make sure that we're finding all of the TDEs out there. And I think there are a couple of clues that maybe we have some selection effects in these optical sky surveys. And one of them has to do with the host galaxies of TDEs. So this plot here is showing you something about the host galaxies. So it's two tracers of star formation on very different timescales. On the y-axis here, you're tracing star formation on timescales of like basically ongoing star formation. This is H-alpha emission, which is only excited by hot O and B type stars. And on the x-axis here, you're seeing long timescale star formation tracers with H-delta and absorption. This is essentially tracing your A-type stars, which live for longer. And so you can see there's this tail of sources. These are what we call post-starburst galaxies. They've gone through a recent burst of star formation, but they're no longer actively forming stars. And if I overplot where the optical TDEs lie, you can see that there's a ton of them in this green box down here. And it turns out if you do the numbers, optical TDEs are about 20 times overrepresented in post-starburst galaxies, just relative to the rate of how often post-starburst occur in SDSS. And so this was kind of a puzzle. It's a question of, are we learning something about what drives TDEs? For example, maybe galaxy mergers both induce post-starburst-like behavior in your hosts and drive more stars into your nucleus? Or is this some sort of selection effect against finding TDEs in other sorts of galaxies? And so to answer this question, and this is kind of motivating the work that I've been doing, I want to go into the infrared band and tell you about how you can see the dust in the nuclear environment around supermassive black holes. So in 2016, there was this first detection. It's actually a series of detections of what we call dust echoes around supermassive black holes around tidal disruption events. So what happens is you have your optical flare that's giving you your kind of intrinsic emission from the TDE. And this heats up the dust in the nucleus, and that dust then radiates thermally and produces this echo. And the light travel time is what gives you kind of the difference in timescales that you see here. And so what a group of us at MIT have been really interested in doing is what happens if you cover your entire sightline in dust. Essentially, what we would expect is that you attenuate your optical and UV flux, and you boost your infrared flux, giving rise to basically an infrared-only flare. So are we missing TDEs happening in dusty nuclear environments? And so with Christos Panagiotou and Kishle Day, we have been working on trying to go out and find these events. And so I'm showing you an example of a TDE that we found in a nearby galaxy. And this is kind of highlighting the methodology that we use to do this. This is difference imaging, which is really commonly used to find transients. But I just want to highlight that, from looking at these two images alone, you can't really see that there's a clear transient. But when you subtract them, you see a very clear nuclear transient here. And this was work that Christos published in 2023. And it turns out that this source is actually the closest TDE we've ever detected. And it was completely missed by optical surveys. So this is kind of suggesting that potentially we do have an overlooked population of infrared selected TDEs. And so what I did during my PhD was I went out and I looked for a full sample of these sources. So we did a volume limited search within about 200 megaparsecs. And the result was 12 high confidence TDEs, all of which show the same signature of a bright infrared flare. And then in the bottom here, you can see the optical light curves. And essentially what the takeaway is that there's basically no optical flare that we're detecting from these sorts of sources. So this is kind of confirming our picture that in dusty nuclei, you can see TDEs that just look like infrared transients. Okay, so let's revisit this post-starburst plot. So remember, our optical galaxies sit down here, or our optical TDEs primarily in post-starburst galaxies. And when I overplot the infrared sources, what you can see is that none of them lie in post-starburst hosts. So if I were to amend this statement at the top, I would say that infrared TDEs do not prefer post-starburst hosts. Now that is very intentional in the wording that I use here, because I think that the post-starburst preference in the optical is real, and we do have an overrepresentation of TDEs in post-starburst galaxies. But I also think that if you want to find TDEs in star-forming galaxies, which is primarily what we're finding, you really need to look in the infrared. And this is possibly because the the host properties and the nuclear properties might be coupled. This is what this is suggesting to us. The other thing that you can ask me is, well, how common are they? You found 12 and you told me there were 200 TDEs. Yes, we found 12 in a 5-year time span in a very small volume of the universe. And so when you work out the numbers, and this is just a luminosity function, so asking how many there are at each brightness, it turns out that we're actually at a very comparable rate to what's found in optical samples. And if you assume that these are disparate populations and you add their rates together, we're kind of reaching closer to what theory is predicting for TDEs. So solving another problem that I didn't even mention to you at the beginning. The other thing is that you might be asking, where's our high luminosity or high mass cutoff? And so because we were in a very small volume of the universe, we're not seeing these very rare luminous events, but we have a postdoc working with us at MIT who is actually studying specifically this high luminosity regime. And she's actually finding that we do see a cutoff. And this is from that event horizon suppression. And so keep an eye out for her paper. It should be out soon. But that's basically confirming that these are TDEs. Okay, so with the rest of the time, I want to focus on what are we learning from these infrared TDEs. And in particular, I want to talk a little bit about their nuclear environments. So one of the things that AGN folks have been really good at doing for many, many years is using the mid-infrared band to probe the kind of dust in the nucleus and understand how AGN are fueled from this like dusty torus. And I show you this schematic in particular because I think it highlights the complexity that the torus is not some donut, but it's really this kind of dynamical structure that's actually extraordinarily complex. And in particular, what I want to highlight is that the mid-infrared band is a powerful probe of the nuclear environment. So this is a sample of TDE, or sorry, this is a sample of AGN studied in the mid-infrared. And you can see kind of one very key difference here, and that's at the 10 micron level. So all the gray sources are type 2 AGN, where you don't see broad lines, and we think you're looking through the dusty torus. And the black ones here are type 1 AGN, where you're seeing broad lines, and we think we have a kind of face-on viewing angle. And you can see that this feature at 10 microns, which is the result of opacity from silicate dust, it's very different between these two populations. And this is suggestive essentially of that viewing angle hypothesis. And you can actually use this to kind of trace the properties of the dusty torus that you're looking at. And so what my collaborators and I have been doing is trying to use JWST and similar observations of these infrared selected TDEs to do the same sort of thing and probe their environments. And I want to remind you that probing the environments around dormant black holes is extremely difficult. And so this is actually what we found. And I also want to say that, we thought we were finding really heavily obscured TDEs that we were only seeing in the infrared. And so you might have been thinking, and I also thought this, that we would actually see silicates in absorption. And it turns out that actually all of our silicates are in emission. So this is telling us that we are not looking through like a dense dusty torus or even like a really dense dust in the host galaxy. Instead, what this is telling us is that we're seeing kind of optically thin emission from dust. And I should highlight here that optically thin depends on what wavelength you're talking about. And here I'm specifically talking about the mid-infrared band. So optically thin to its own emission, essentially, is what I'm saying. And it turns out that if you actually go and you plot the strength of the silicate features of these TDEs versus what's typically seen in AGN, you get something that looks very different. So this is just the two silicate features, so one at 10 microns, and there's also another at 18 microns. Positive values here indicate emission, negative indicate absorption. And you can see that a lot of the AGN are kind of clustered at lower values at something like 0. And that's primarily because of the clumpiness of dusty tori. And our WISE TDEs sit in a totally different part of parameter space. And I think really what this indicates is that dormant supermassive black holes have different environments than AGN. And okay, that's not terribly surprising, but I think this is pretty exciting because it's telling us that we can actually probe the environments of dormant supermassive black holes kind of for not necessarily the first time, but like in exquisite detail with TDEs in particular. And one thing that I want to highlight, something that I've been thinking a lot about lately, is that if you look at where this emission is primarily coming from, it's primarily coming from very close to the supermassive black hole. And if you look at one of the JWST images, it has an exquisite PSF. It's like 0.3 arc seconds. That's still 70 parsecs. So that's quite large. We're never really going to be able to resolve that in the mid-infrared, at least with ALMA, sure. But in the mid-infrared, it's very difficult. And so something I've been really interested in is studying the time dependence, because these TDEs are like, you turn them on instantaneously, nearly, and then they decay over time. And what you actually see is that they light up different parts of the nucleus. So this is showing you essentially the temperature of the dust as a function of time from the time that the TDE turns on to 10 years later. And so I'm excited about using the time dependence of TDEs and the mid-infrared band to try to probe the nuclear environment in good detail. And this isn't just a toy model. Well, it is a toy model, but we've actually applied it to our data. And what we've been able to see is that you can reproduce the JWST spectra with this time-dependent emission model. And actually, you can get pretty good fit to the overall data. It's a little bit complicated, and I'm happy to talk about dust physics if you want to ask me. But I just want to say it can reproduce the spectra. And now I think what the next steps are to try to kind of sample at different times and see how the spectrum actually evolves, and that will give us a good probe. Okay, there's one thing else that I want to highlight from the JWST observations, and that's that there's actually these narrow lines from highly ionized species. And this is basically telling us that these infrared transients have to be powered by black hole accretion, which if you combine that with the fact that I told you they don't have AGN environments, I think that essentially tells you have to have a TDE. So this is a really nice kind of piece of confirmation that what we're seeing in our infrared light curves are tidal disruption events. And just to highlight this, in the optical band, people commonly think about BPT diagrams, so ratios of different line strengths to probe the underlying ionizing spectrum. And we can do the same thing in the infrared. So this is basically two higher ionization lines over a line that is primarily produced by star formation. So if you sit in the bottom left part of this plot, your primarily star formation is driving your ionization of your gas. And if you sit in the top right, you're seeing basically accretion-driven ionization. And so these are for known star forming and AGN systems. And if I overplot where the WISE TDEs sit, they sit much closer to this AGN population, telling you that you have black hole accretion going on. And right after I put this paper on the archive, actually similar work was, theoretical work was done to show with photoionization models from TDE, predicted TDE spectra, that you should actually, around the same time, start to see the same sorts of features, that you should be ionizing your nuclear environment and producing these sorts of lines. So I think this was a really nice confirmation. I was really excited to see this paper come out. Okay, so what have we learned from the study of infrared TDEs, and what's next? So one thing is that we can use the mid-infrared spectra to probe the environments of dormant black holes. And so what I'm excited to do now and to start thinking about is not only these like time series of TDEs, but also studying different sorts of transients. So in particular, we know very little about how AGN are triggered. So how we go from a dormant supermassive black hole to something that's rapidly accreting. And so I'm part of a HOPI of an approved JWST Miri Cycle 4 program to study a turn on AGN. And I think that will help us understand, I think, some of the forming of a dusty torus, essentially. And the other key thing that we've learned is that we can identify TDEs with infrared light curves alone. That's essentially how we did our study and picked out those 4 sources, that actually 12 sources in total, but we narrowed it down for the JWST TAC. And what we showed is that these are all tidal disruption events. And the reason why that's, I think, really exciting is that it sets us up well for the next generation of observatories. So in particular, I've been getting more and more excited about the launch of Roman, which is expected to happen next year. And in particular, Roman's going to do this high latitude time domain survey, where it's going to survey 18 square degrees of the sky fairly regularly. In its first year, it's going to do a pilot program where it's samples, I think, 8 total times. And this is going to be a treasure trove for finding transients, especially at the near infrared wavelengths. And so one thing that I've been working on lately is trying to predict what we should be seeing in Roman for obscured sources, and how can we use this to complement, say, Rubin's efforts in finding optically selected TDEs. So this is just showing you the predicted near infrared spectrum based on those JWST models. at different redshifts. So you can see we're kind of redshifting out of the Roman band quite quickly. But Roman's exquisite limits means that we can probably push to about redshift 1 to detect obscured TDEs. And this is, I think, really important because we know that the host galaxies and the environments around supermassive black holes evolve throughout cosmic time. In particular, as we go to the high redshift universe, which is where Rubin and Rubin promised to take us for transients, there's going to be more dust and more star formation and environments that are quite different than our local universe. And so I think being able to probe that evolution is going to be really critical to getting a full census of TDEs and kind of understanding the total population. Okay, and then on the Rubin front, the one thing that I want to mention, so this is one of the first light images, is that looking for TDEs is in general a very arduous task. So this is just a pie chart of how many TDEs occur in the nucleus of a galaxy. You can see primarily you actually see supernovae, and TDEs make up only 1%. So this is what TDE transient finders look like. And so in order to reduce the haystack, what they do is they make cuts on the sort of optical properties that they expect from TDEs. And primarily what they cut on is that TDEs should be blue in color and they should not redden with time. So that's what's showing you in this red circle. We're kind of to the left of the plot and right around 0. And that's mostly to rule out supernovae. And that's great if you want to increase your detection rate, but it's also going to cut out things like mildly obscured TDEs, where if we have kind of intermediate amount of dust, we'll see an infrared flare and a red TDE. So one of the things I'm excited about is trying to use Rubin in connection with Roman to actually look for this kind of mildly obscured population and try to understand, are we missing more TDEs, and B, are these infrared and optical TDEs populations really disparate, or is there kind of a smooth continuum between them? Okay, the last thing that I want to do is when I was invited to give this talk, I think it was mentioned that I could mention some of the advocacy work that I've done during my PhD. I've been involved in a number of different projects, but one that I wanted to highlight here is one that's near and dear to my heart, but also hopefully applicable to you and your students, which is a program called PhysGap. It's the Physics Graduate Application Assistance Program run out of MIT. And essentially what we do is we try to help incoming and applicants to the MIT Physics PhD program to put their best foot forward and kind of demystify the grad application process and make it more equitable. And so we run a series of webinars. We also hold office hours, and we provide one-on-one mentorship. So I would be happy to share this flyer and so that you all can share it with your students and hopefully make use of this program. Okay, so with that, I just want to say I think my key takeaways are that time domain astrophysics is challenging our canonical picture for how black holes grow and also unlocking new populations of dormant black holes and allowing us to study their demographics. Thanks. Happy to take questions.
Any questions?
Can you go back to the full animation of the time domain?
Yes. This one?
Yeah, what does this actually about the geometry of the?
Yes, this is a spherical geometry. So that's also the other thing is that, like, if you want to measure dust covering factors, for example, you need to be kind of careful about your time-dependent effects, which I think is something we as a field have not been doing a good job with.
Can your model do more complicated?
Yeah, sure. It's not currently built into it, but I'm working on, I think, in order to really use this for Roman and stuff like that, there's other dust elements that need to be improved. So this is a really simple treatment of dust, and there's a number of things. Yeah, thanks.
Any others?
I want to just ask a question about the graduate applications.
Yeah.
So congratulations on doing that. But one of the things is nowadays it's just an overwhelmingly huge number of applications.
Yeah.
And what you're taking on is a very big job. I wonder if you could comment on how you balance.
Yeah.
How do you find time to do something like that?
Well, that's a good question. I think that So PhysGap is a program I've been involved in since very early on in my PhD, and it's one of the places where I feel like I've made the most change. And so for me, it's extraordinarily meaningful. And you can see like it, even if it doesn't help an applicant get into MIT, they're using the advice and sort of things that we give them to use to other to get into other schools. So I think it's important to make time for it. The other thing is that over time we've seen the program grow. And so the number, for example, the one-on-one mentorship program usually gets over 100 applications per year. And we usually have capacity for like 80 students or so. And that's based solely on the number of MIT physics graduate students that can mentor students. So what we've developed was this office hours program. And this is primarily so that people have like 10 minutes to chat with someone and ask some questions. And so that we're not turning away a ton of students. And so this is really, I think we've increased our capacity by like 50% by adding this office hours program. So
How big is that? How many physics graduates do you have at FT?
there's of order 250 to 300. So it's a physics department. So there's of order 40 astrophysics, but there's a ton of other types of physics as well. So it's actually 80 people out of 250 is a large population of the graduate students that are involved in this effort. So yeah, and the department actually like really encourages it. And like we regularly meet with the chair of the graduate admissions process to make sure that like we're providing recommendations from the grad students and they listen to them, which is really wonderful. So yeah.
On the same thing, do you track outcomes?
Yes. However, we are like currently in the process of putting together like a 5 to 6 year report. So I don't have the numbers off the top of my head. They're very small number statistics. It seems like maybe the rate is higher, but also there's biases in that like our program starts over a month before the deadline. And so we're also getting people who, know about the program a month before the deadline. So, but it does seem like the program is helping people. Yeah.
Any science questions? Okay, then let's thank our speaker. Should be here, should be around today, and I think there are still some open spots. So if you want to have a chat with her, Diana.